Hi, I'm Robert Robson with the Periodic Periodical, and today our topic is dimensional analysis. So, how does dimensional analysis work? Which dimension do you analyze? The third?
Hello, Robert. No. Dimensional analysis helps you arrive from one unit of measurement to another. Say, for example, length, mass, or even volume.
So you were telling me that with this method, you could convert one unit of measurement, say 35 meters per second, to something like miles per hour.
Of course! That is very easy. First, you must make sure you know at least some basic prefixes, such as deci, centi, milli, or kilo. And also, you must know how to convert from English to SI units in order to facilitate your conversions.
Could you show me an example?
Sure! Let's take your 35 meters per second. We then go and put 1,000 meters per 1 kilometer. Here we have basic prefixes. Then we go 1.6 kilometers in 1 mile. We then put 60 seconds in 1 minute, and then 60 minutes in 1 hour. And this equals a whopping 78.75 miles per hour.
Oh wow, looks like I need to slow down a bit when I drive. Well, anyways, do you think you could remind the audience also on naming compounds in chemistry?
Oh, that's easy. First, you must decide whether it is a covalent or an ionic compound. If it is a covalent compound, it will be made up of 2 nonmetals, and the more electronegative atom will be ending in "ide," as well as you should be using numeric prefixes such as mono, di, or tri. Now, if it is ionic, it'll be a nonmetal with a metal, and the anion will be ending in "ide." And then if you have a transition metal, you have to make sure you put its charge in Roman numerals.
Wow! That certainly is a whole lot of rules. Well, thank you very much for that explanation, Kane. After a short commercial break, we will be back with an exclusive interview with Dr. Soulflower.
Hello there and welcome back. This is Kane reporting for Periodic Periodical. I'm here with Dr. Heterocyclic Soulflower, who is a leading expert in the thoroughly under-investigated yet critical field of introductory general chemistry. First off, there's been a highly important, if not so recent development in your field called the balancing of chemical equations. What is a chemical equation, and can you balance it with your hands, or do you need some specialized equipment?
Now, a chemical reaction is actually a representation of a chemical reaction on paper, where certain chemicals or reactants are mixed together and then other chemicals or products are formed. No special equipment is needed.
Wow, that's impressive. So what is the law of conservation of mass?
The law of conservation of mass states that matter can neither be created nor destroyed. So when we're applying that to this topic, that means the number of atoms for a specific element has to be the same before and after a reaction occurs.
Makes sense. Well, I say you thoroughly destroyed the matters of interest of our audience. I'd like to move on to acid-base reactions. Would you mind telling our audience what an acid is?
An acid is chemically defined to be any substance that releases positively charged hydrogen ions when put in water.
That's right. Well then, if acid and bases are opposites, bases would be the thing that absorbs hydrogen ions in water, right?
Not quite. Bases also produce a certain product. Instead, they don't absorb anything. Instead, they produce negatively charged hydroxide ions. These, in turn, bond with the positively charged hydrogen ions released by the acid and form extra water molecules.
Alright, well, thank you very much for this interview, Dr. Soulflower. Viewers, make sure you go follow him on Twitter.
Thank you, Kane and Dr. Soulflower. Now, moving on. I'm out here today with Lorenzo Romano Amadeo Carlo Avogadro di Caregna e di Cereto, better known as Avogadro, and he will be filling us in on his latest discovery. Now, since our guest doesn't speak a lick of English and he's dead, he went ahead and handed me his transcript, so I will be relaying the information myself. Following recent formula derivation and experiments, I have concluded that there is an undeniable relationship between gases, specifically that equal volumes of all gases at the same temperature and pressure have the same number of molecules. Mathematically, this can be expressed as V1 over N1 equals V2 over N2, where V represents the volume of a gas and N represents the number of moles of that gas. When rearranged, this can be used to calculate one of the other missing variables. For example, if we have 2 volumes of a gas A, where there are 3 moles of that gas, and 3 volumes of gas B, then we can solve for the number of moles of gas B, which is 4.5. This, unfortunately, only holds true on paper, and real gases show small deviations from this ideal behavior. Thank you, Avogadro. Next up, we have a guest named Jermaine Hess. Once again, we're exploring physical chemistry laws, this one having to do with heat transfer. Jermaine. Thank you, Robert. Now, according to my most recent observations, I have unveiled that the entropy formation in a given reaction will always be the same, regardless of the pathway it's taken. This can be given by the overall equation delta H of the reaction equals the sum of the H of the products minus the sum of the entropy of the reactants, as well as this indicating the standard state values. In layman's terms, if you are trying to form a substance from any other substance, then no matter how many reactions you must first go through to receive your final product, total transfer of energy will inevitably remain the same.
Welcome to another exclusive interview. I'm here with Dr. Barman Kane. And first of all, I would like to ask you, how would you define light?
Well, light can be defined as a transverse electromagnetic wave that can be seen by the human eye. And this is very important because each element gives off a specific color of light, which is directly related to the amount of electrons each element possesses.
Now, could you define the electromagnetic spectrum?
Yes. See, the electromagnetic spectrum is a collection of known frequencies and related wavelengths that have known photons.
And we are back here with Dr. Kane. Sorry, we had a slight chemical explosion in our last room, which caused us to find a new room. But anyways, we're back. And I would just like to ask you, what is the main relationship between elements in the same group?
Well, you see, they share the same characteristics, and this is due to the fact that they have the same number of valence electrons.
So, you mentioned these trends across the periodic table. What is an example?
So, to start with, we can look at atomic radius, which is the size of an atom. The trend across the periodic table with atomic radius is, as you move down the table, the atomic radius will increase because shells are being added. And then, moreover, as you move to the right of the periodic table, the atomic radius will decrease because the proton to the right had one, or the element to the right had one more proton than the one before it.
So the audience has just asked about ionization energy. What can you tell us about that?
So ionization energy is the energy required to remove an electron from the outermost shell of an atom. When observing this periodic trend, we'll see that the further away an electron is from the nucleus, the easier it is to pull it away from, or the easier it will be to pull the electron away.
Well, thank you very much for this interview, Dr. Kane.
And if y'all would like any more information on topics such as these, you can find me on Twitter at @TheRealistBarMonsterCubane.
And next, reporting on the different ways atoms can bond. Florina Oxina. Florina, can you tell us what's happening out there?
Alright, if you look closely behind me, you see a covalent bond. In this covalent bond, the electrons are being shared between the two atoms. Also, if you look closely, you'll notice that the two atoms are nonmetals.
Love-hate. Sounds like my wife and I. Well, would you look at that? Would you let us know what's going on to the right of the covalent bonds?
Oh, that was an ionic bond. Let's go check it out. So here we see a metal and a non-metal. They're not sharing electrons like the covalent bond did, but they're transferring them. And since fluorine is a more electronegative atom, it's actually taking an electron from lithium. Now back to you, Robert.
Wow, well, that is something else. Thanks, Florina. I hope you had a good time out there checking out all those bonds. What are the odds that they would all occur at the same place in the same time? Now, to Dr. McLovin on Vesper Theory.
Yes, Robert, I'm here right now with so many compounds with different molecular shapes. As you can see, they have many variations, but most of these all can be explained by the Vesper Theory. Okay, so the Vesper Theory states that atoms, when forming bonds, choose different configurations that best minimize electron repulsion. Okay, look at here. Okay, this is boron trifluoride. See? So it is a member of the trigonal planar arrangement species. You can see how it optimally configures its shape using the bond angle 120 degrees. This way, the fluorine atoms are spread out as far away from each other as possible. Wow, look at that! It's another compound of the trigonal planar arrangement species. It looks rather weird though. This compound is called tin-2 chloride. It has 2 chlorine atoms bonded to a tin center. However, its bonding atom is not 120 degrees like the boron trifluoride compound that we saw. It has a lone pair, so the lone pair is very electronegative. It repels the bonding pairs more than they repel themselves. So as you can see, the ideal bonding angle here is 95, which is way less than 120 degrees. So you can draw molecular shapes by yourself too. First, you draw the Lewis structure of the compound. Second, you assign an electron group arrangement by counting all of the electron groups, bonding and non-bonding, around the central atoms. Third, you predict the ideal bond angle from the electron group arrangement and the effect of any deviations caused by lone pairs and double bonds. And then you add all that together and draw that molecular shape like a pro. My name is Dr. McLovin. Back to you, Robert.
Well, thank you, Dr. McLovin. Up next, we have an exclusive interview with Dr. Grillin.
Welcome back to another exclusive interview. This is Kane Hussein, and we're here with Dr. Grillin. We're happy to have you.
It's a pleasure.
So, could you give us some more information on the valence bond theory?
Well, of course. So the basic principle of the valence bond theory is such that the covalent bonds form when orbitals of 2 atoms overlap and a pair of electrons occupy the overlap region. I would also like to add that there are 4 themes of the valence bond theory. The first is the opposing spins of the electron pair, next the maximum overlapping of bond orbitals, then hybridization of hybrid orbitals. Lastly, the features of the hybrid orbitals.
I would ask you to elaborate a little bit more, but we have many topics to discuss. Please give me a little more insight on the molecular orbital theory, please.
So the molecular orbital theory adequately explains magnetic and spectral properties and both understate the importance of electron delocalization.
Interesting. I heard there was also a model associated with a molecular bond theory. Could you explain to me a little more about it?
Sure, so the molecular orbital model is a quantum mechanical model that is similar to the ones for atoms. So the 3 main themes of this theory are formation of molecular orbitals, the shape and energy of H2 molecular orbitals, and the electrons in the molecular orbitals.
Well, thank you very much for that interview, Dr. Grillin. Now back to you, Robert.
Well, thank you, Kane and Dr. Grillin. This is Robert Robson from the Periodic Periodical, signing off. I think I left my electron somewhere.
Are you sure?
I'm positive.